Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. It's my pleasure and honor to introduce our guest speaker for today, Steve Young. Steve is currently professor of information engineering at Cambridge University and head of the information engineering division. However, he has very close ties to Microsoft, not only because he has advised many students who are now Microsoft employees, but he co-founded and was the technical director of Anthropic, which we acquired in 1999. So he was actually a blue badge, full-fledged Microsoft employee for a while as an architect, but he decided to go back into academia. So he went back to Cambridge University. He has had an illustrious research career in the area of spoken language technologies, from speech recognition, speech synthesis, to more recently dialogue management. Among kind of his notable contributions, he's the inventor and author of the HTK toolkit. He's been doing work on POMDPs lately, which has been gaining a lot of speed. With this kind of career, you would expect a lot of distinctions, and he does have them. He's a fellow of the Royal Academy of Engineering, the Institution of Electrical Engineers, and so forth and so forth. I think you guys have all seen his bio. So without further ado, Steve Young.
Okay, thank you. So I'm going to talk today about some work we've been doing for the last few years now at Cambridge, which is kind of to one side of the speech recognition work, but arose out of initially out of the assumption that however hard we worked on speech recognition, it was never going to be perfect. So how can you improve a spoken dialogue system given a recognizer which is going to make errors? That was the sort of the original motivation. And since then I thought sort of a little bit more about what a human-computer interface should be doing. And I'll just say a little bit more about that in an introduction about why I use POMDPs for HCI. And then I'll just quickly go through a simple example which you may find too trivial to bother with, but it's to try to illustrate for those who haven't really thought about using what POMDPs are and how you might use them in an interface. It makes it perhaps a little clearer than the speech case, which is the complexity sometimes hides the kind of the big picture. And then I'll talk about how you scale POMDPs to big problems like spoken dialogue systems. And then give as a way of example, talk about the system we've started working on first about 5 or 6 years ago, something called the hidden information state system. And then very briefly at the end, I'll say something about a more recent system, which is a Bayesian update system. And then I'll wrap up. So why use POMDPs? Well, if you're going to build an interface which is going to be robust, whether it's speech or any kind of human interface, you're going to have to deal with uncertainty. And I think if you don't model uncertainty explicitly in the way you manage a dialogue system, you're never going to be able to do very well. And as part of that, I think it's important to be able to track what the user's trying to do. Because the only way you're going to interpret something which is noisy and probably ambiguous is if you've got a pretty good context in which to interpret it. The third thing is that communication is always trying to serve some goal. So it's good if you can quantify those goals, and then you've got something to optimize. And then finally, you need to be able to adapt. So that suggests that however you build a HCI interface, it really needs to be mostly parametric and not just handcrafted rules, because otherwise you're not going to be able to adapt either to rapidly changing environments in the near term or even in the long term. One of the things that always strikes me about most deployed spoken dialogue systems is that people put a lot of work into them on the day they install them, and then they might run for 6 months, a year, or several years, and the performance doesn't really change with time at all. There's no sense in which the longer you use it, the smarter it gets. So I'm going to argue the POMDP framework is the natural way to deal with all of those issues. So let me very quickly, sometimes people stop me when I do this, and I spend the entire talk with this example, which would be a bit sad. But an iPhone is a gesture, uses this gesture interface, and sorry to mention it, having an iPhone example in this particular building, but apologize for that. So think about the interface for suppose you've just taken lots and lots of photos, and you want to quickly skim through them and delete the ones you really don't want to keep. The current iPhone interface is a bit clunky. You have to select the photo, select the delete key, then I think you've got to confirm that you really want to delete it. So suppose you just want to have an interface which is really quick and consists of just swipes. So swipe left, swipe right, swipe down to delete, okay? So in other words, something that looks like this. And delete and so on. Now the problem with this, of course, if you do it quickly, is that you'll make errors, probably, and you'll start to delete the things you don't intend to delete. Now, traditionally, remember this is a toy example for illustrative purposes, so don't start saying that they don't do it that way. Just imagine that the gestures are in this case, are just identified by the angle they make. So you could divide up the compass like this. The blodges, the green blodges are forward gestures, backwards gestures, delete gestures. And of course, you'd have to have something in the device which is going to measure the angle, and that's going to make errors. So this has made some sort of error. And the usual way to do this in the classic sort of framework is you say, okay, well, we'll sort of use some kind of pattern classification approach. We'll record some data. We'll annotate it. We'll get some distribution, some distributions that might look like this. We'll put some decision boundaries in there, and at least in some sense, we're making an optimal decision. We could even put some risk in there. And so when we get this gesture that we don't know about, we compare it with the decision boundaries, and we decide that's a backwards gesture. And then we can go a bit further than that. Since we've got the distributions and we know what the overlap is, we can compute the probability of error and compute some kind of confidence threshold from that. And so then we get the actual application is typically hardwired. So it has something maybe like this: recognize a backwards gesture, check the confidence. If it's greater than some threshold, move back maybe, otherwise do nothing. So that's a kind of classic implementation strategy. And as far as I know, that's how really most of the deployed, certainly spoken dialogue systems work in essence.
Steve, so in that case, if you make a deletion, you have
interrupting me, isn't it?
If you have easy recovery strategy, if something delete, you can simply have one gesture to recover.
Yeah.
Then you don't really have to
deal
with all this.
I'm trying to illustrate why POMDPs are good. I'm not telling you how to make an interface. Okay. But even then, let me continue. Okay. So what's missing? Okay, there's no model of uncertainty as such. The iPhone is not trying to track what I want to do. It's just responding to my inputs. Okay. So it's not trying to track it has no belief about my intentions. And there are no quantifiable objectives, so in some sense the decision making is suboptimal. Now, this is a very simple example, so what quantifiable objectives could there be? Well, as we'll see, we could code the risk in terms of rewards and so on. So how do we deal with that? Well, the first thing we need to do is model uncertainty, and we use Bayes' rule. our old friend Thomas Bayes. So if in graphical networks term, what we might do is we might treat the problem like this. We say, okay, I'm going to imagine that the user has 3 possible intentions here: to move backwards, move forwards, and delete. And so, but the system doesn't know what they are. So we'll say that's a hidden variable, and we'll say that the probability of having some intention at time t, it depends on the intention at time t-1, and also the last thing the machine did. Now you might think in the delete example, but surely these are independent events. Well, they're not really, actually, because typically people scroll forwards rapidly through the photographs. They'll go past the one they see and think, oh, I really don't need that, and they'll tend to go back, and then they'll tend to delete. So there is structure, okay? Not a lot, but a little bit. But of course, in the speech example, there's much more structure than that. And then you model the. So then you say, well, I don't know what the actual intention is. So I will represent. I'll compute a distribution. I mean, this is what this is what the graph means. Of course, this is a hidden variable. So all we ever know about this variable is its distribution, and I'm calling it B rather than P. But this is the probability of each state S, and I'm calling it B because that's going to be my belief. And you'll see later that the critical thing is that the actions that the system takes depend on B and not S. So now I have this set up. So when when we move to a new time slot, we can compute a new belief by looking at the data. We're not classifying the gesture anymore. We're just looking at the angle it makes, and based on that angle and this observation distribution, we can update the belief distribution. And we are not going to, as I say, we're not going to use this as some kind of threshold, as some kind of adaptive thresholding system. We are going to base what the device does on the entire distribution and not do any kind of maximum likelihood estimate of the intention. Okay, so that's the belief framework, and this is the framework that is implied in when we say it's a POMDP. Of course, the second part of the puzzle is the optimization bit of goals, which depends on Bellman's optimality principle, which comes in many forms. This is just one of them here. And essentially, it's a recursive equation which says that the key idea is that you can associate with each pair of belief states and actions a local reward. And then what you want to do is treat the whole dialogue or sequence of interactions as an entity and compute some total reward for the entire interaction. And Bellman pointed out that if the process is Markov, you can compute an expected value for any belief state B. You can compute the expected value of total reward from that belief state by a recursion that looks like this. As I said, it comes in different forms, but in this case, it's just saying it's a recursion over. Essentially, it's the local reward plus the expected reward in the next belief state. The prime just means next time slot here, and it's an expected value with respect to the observations. And the max is you can use to optimize, find the optimal reward and hence the optimal policy. So in terms of our problem, so set out the graphical model. Let's treat it as a DBN, which it is. Extend it out over the t time slots. And then what we're saying then is, okay, I'm going to have my policy, which is that instead of this hardwired decision network, I'm going to say each action depends as a function of the belief state, not the most likely state, but the distribution over all states. And so we get this sequence of actions driven by a policy, and then we can sum the local rewards to get a total reward, and this is the expected value of this is V, and then we can effect various algorithms for doing this, but we can essentially iterate. We can use the policy to compute the reward, and the maxing here allows us to to adjust the policy to incrementally increase the reward. And if we do this iteratively in a process called reinforcement learning, we'll end up with the optimal policy under certain constraints which aren't too interesting. Okay, so if we do that for this simple example, then I've got my user's goals. These are the things we don't know, but we assume they're in the user's head. We've got the system actions. We define some rewards. So let's give a modest, small reward for moving in the right direction, a bit bigger reward for deleting when we want to delete, but then give a big negative reward for deleting when the user didn't want to delete and just wanted to move forwards and backwards. Now you can change these rewards, of course, to suit your design criteria. That's a design option in effect. And then we can iteratively optimize. Now, this is just a toy example, right, to illustrate the idea. And so I didn't actually compute probability. Obviously, this depends on probability distributions for the transition function and the observation. And I didn't train these. I just chose some plausible-looking parameters just to illustrate how this might work. And then also set up a simulator to generate gestures with error rates varying from 0 to 50%. And the vertical axis here is the average reward per turn. So, and there's a zero axis here, so going below the zero axis is probably bad news. And this is a simple but reasonable handcrafted policy which just uses a fixed confidence on the threshold. And it basically comes down pretty rapidly as the error rate increases. So if you go to a party and you drink enough, you really wouldn't get very far with this interface. Now, if we use the POMDP framework and train it at a fixed 30% error rate, you get a curve that looks something like this, whereby we see we've made it more robust at high error rates, and we've lost a bit at low error rates. And indeed, if you look at the policy, you find it's basically become risk averse.
So what do you mean by training? You said that you're not going to train the parameters.
No, sorry, the policy, but I'm not going to train the parameters of the transition probabilities, but I am going to optimize the policy. Yeah, the training here means the,
so there's a single POMDP.
So I used Q-learning, and I actually used the user simulator to train with Q-learning, and I set the error rate to be 30%. Yeah, problem? Yeah.
So Q-learning over what? Over observations?
Of the policy. I'm trying to learn this mapping from belief states into actions.
So Q-learning over the beliefs directly.
This is a POMDP, yes.
Okay.
Oh, sorry. I mean, not literally. I mean, yes. I don't mean literally Q-learning. Sorry. I use a Monte Carlo-based training method, which is doing an approximate POMDP learning algorithm. It's not important. It's a reasonable algorithm.
So in the original handcrafted setup, there were some thresholds that had to be set, having to do with confidence and understanding.
Yeah, just one.
Okay.
Just one threshold, yeah, and I just fixed the reasonable value.
Okay. Then in this POMDP setup, there were several different rewards that had to be set up.
Yes.
So are these rewards that you set by hand, are they qualitatively different from the thresholds that we set by hand before?
Well, they'll end you up with a different operating point, and I haven't explored this. And I'll tell you, this is not a serious example. This is tutorial, Jeff. This is motivational. Okay, we're not trying to design and persuade you that this is the way to produce an iPhone interface. So if you want to disbelieve the results, fine. We can go on to the real results for speech systems later where we get the same performance. I'm trying to illustrate that the different way of approaching the problem.
Will the results with the speech systems involve setting rewards, or is that also something
Yes,
else?
but very straightforward reward. We just have dialogue systems, and we give a big reward for getting the right answer and zero for getting the wrong answer, and we penalize, give you a small penalty every turn keep it going along. So, and we've not tried to optimize that or say what do you really want from the design. We just typically use that kind of straightforward big reward at the end.
Do you have to, in order to apply this, do you actually have to know what the error rate is?
Do I have to know? Well, okay, let me just put the other curve on. Okay, if you did know what the error rate was, and you trained the policy at different error rates, and you updated the observation parameters to match the error rate, you get a curve like this. Okay, and so this is a kind of upper bound on the performance you could get with this kind of setup. Okay, now how you would know what the error rate is a priori, is a different issue. But that's an upper bound on the performance for this particular setup. And it's a toy example, it's just meant to be tutorial. The point is, one of the things that's making the difference here is that the system is using the transition probabilities to bias, implicitly adjust its thresholds. Remember, because it's updating its belief model based on the transition probabilities, and that makes the difference. And that's one of the reasons why you're getting a significant difference between this and this. Okay, so the bottom line of this example is simply that don't think of a speech system as being a command-driven interface that you speak commands and the system responds. Think of it as being a system where the system is just trying to track what the user wants to do, and it's regarding inputs as observations that it's using to refine those beliefs. And then the policy training stuff is almost secondary to that. But that's the key difference in terms of designing an interface. Okay. So, well, I've just recapped that. So that's the basic idea. Now, the problem, of course, with speech or a speech-based system is it's pretty complicated. So I only have in my iPhone example, I only had 3 possible states. And there's a whole load of packages which will train POMDPs in different ways for small state spaces and make a reasonable job of it. The big problem comes where you have a very large state space and a large action space. So how do we set up a system where we can do Bayesian inference tractably in real time over this very large state space, and how can we actually optimize policies as well using reinforcement learning, which tends to get very difficult in large systems. So, but if we could do that, I'm arguing that this is a really rather principled approach to handling uncertainty and planning, and that's what you need in any kind of interface which is driven by human interaction. So what's the problem? Well, it's the scaling problem. So just to set the context, this is just a generic sort of spoken dialogue system architecture, the one we've been using. And what we do in our systems is we have, so I should say that this is a limited domain application. The domain is actually tourist information we've been working on. So you can talk about things as the user can say things. I want to find a restaurant, the usual stuff. I want to find a hotel. The system I'll show some examples of is actually of an artificial town. We're just about to start. We have now a version for Cambridge that we're about to start making accessible to the public, which has got many more entities in it. But this, in the example I'm going to talk about here, it's essentially about, you can ask questions about hotels, restaurants, and bars in this fictitious town. And we have our architecture is that we convert words into these abstract representations. We have a set of these dialogue acts like confirm and negate, inform, request, and then you have attribute value pairs, which are arguments to these dialogue acts. And we have this as we use this as a well-defined interface to our dialogue manager. I'll play you a little example of a demo system running a bit later, but just in passing, all of the components are statistically trained entirely from data apart from the message generator. And I should also stress that the dialog manager has no application dependent code in it at all. It doesn't know anything about towns or hotels or bars. It's all learned from interacting, learned from data. So the first system then is a hidden information state system. This was built primarily as a demonstrator that this notion of tracking belief over multiple states would give you increased robustness, and not necessarily meant to be the way to do it. It tries to mimic the basic ideas of the POMDP framework. So it takes the speech understanding system as an observation, and in fact we compute an n-best list of these abstract dialogue acts. So the interface here is just a list of all of the dialogue acts that the system can decode from the user's input. And that's what I just did, these kind of abstract representations like confirm near equals tower. So you get a list of those here. This thing is trying to update a belief over a set of states, and I'll tell you a little bit more about the states in a minute. And then we have a policy which generates actions, which gets converted into speech and so on. And we make this tractable by two mechanisms. First of all, we group states into what we call equivalence classes called partitions. So rather than having to compute beliefs over every possible state, we have far fewer partitions. And then secondly, we don't compute the dialogue policy directly in belief space. We map this rather complex belief space into a summary space, which I'll explain a bit more in a minute. And then we implement the policy and also optimize the policy in this summarized space. And then we heuristically map back these much simpler actions into the higher level space. And this basic model was developed originally with Jason Williams, who was a PhD student of mine. So the actual state we record in this system has three factors. The user's goal, that corresponds to the what does the user want to do, move back, move forward, delete. The user's act, that's the last thing that the user said, and a dialogue history. And just to put a little bit of flesh on that, and the goals are grouped into partitions. So what we actually do in practice is we have a list of things which represent possible groups of goals. So represented textually here, just for us to be able to read it. So this is the set of all goals which involves finding a hotel in the east part of town. This is a set of all goals which involves finding a bar in the east, hotel in the west. Something like just find venue is just the goal of finding something. Okay, and this is meant to be a mutually exclusive set. And this is composed with our n-best list, and then we have a grounding state. So any of the entities in any of these partitions will have a state associated with it, and the state is something like it's been queried, it's been grounded, it's been requested, and so on. And this is conventional stuff in dialogue systems. This is essentially David Trown's grounding model. But remember, this is sort of probabilistic, so anything like area equals east can have multiple states. In fact, it's a distribution over all possible grounding states for all possible arguments for these goals. So what we actually do in practice is we take instances of each of these distributions, so a particular partition with a particular assumed last user act and a particular set of grounding states makes a single instance for which we compute a probability. And we compute all of the most likely combinations, rank them and prune them. So over the millions or even billions of potential combinations here, we typically maintain the top 2 to 300 values if you like, and their probabilities. If you work through the maths, you get something that looks a bit like this. So this is the actual belief update, and I'm not going to go in detail in this. In fact, I'm not showing the partitions here. This is for actual states. If you plug in do some more algebra on this, and you have F's divided into partitions, you can get something similar to this. But this illustrates the basic idea. You have
So the partition is done manually?
No, the partition's completely. So I didn't really want to get into this because it's a kind of almost boring implementation detail. We start off with everything in one partition because we don't know anything. The user says something, the recognizer generates all of these hypotheses about might have been said. If there's any mention in any hypothesis about anything like a Chinese restaurant, a cheap hotel, then the set of partitions gets divided so that you can always associate each possibility of what the user said with a specific partition. So this splitting doesn't change the maths at all. It's just a computational device in effect. It would work exactly the same as if you were able to maintain every possible combination and you computed the beliefs individually for each combination. If you look at the equations, what you find is this is B. Remember, B, this is a probability, but you're recomputing this distribution every turn. And this is the old belief, and the prime is the new belief. And so if you look at the terms in this update equation, and this is standard textbook stuff, what you see is these three components. The transition model is just taking account of state changes. And in fact, we assume there are no state changes, so we assume that whatever the user wants, they don't change their mind in the course of a dialogue, and this is a weakness, and I'll come back to that. So you can more or less ignore this. It's basically an identity transform. And then these two terms are the important ones. So this is the user action model, and this says, okay, remember that this S prime here includes the three components: the user's goal, the last user act, and the grounding model. And the grounding model is hidden in here. So this term says, what's the probability of the user saying something, given that their goal is this? So if you're hypothesizing the user says, I want a cheap hotel, and in the particular G here, part of the goal is they're looking for a hotel, you'd expect this to have a high probability. If the particular goal is they're looking for a bar and they say, I want a cheap hotel, you'd expect this probability to be small. And so this probability, and we call this the user action model, this is the thing you don't get with many alternative formulations of this problem. And then the observation model here essentially takes the place of the confidence measure, which is the probability of the observation given the specific user goal.
So just going back to Lee's question, this is just a factorization of the partition set, right?
This is taking if you look at the graphical model, you figure out the relationship, the update equation, and then you substitute in the factored version that S is actually represented as these three components, and you'll get this. And then, as I say, in the actual system, we go a bit further because we group the S's into partitions, which requires a little bit more manipulation.
Getting the boring part of the partition, but so you partition basically at runtime based on things that you hear from the recognizer, if I understood you correctly.
Absolutely.
Does that mean that most
and from the system?
Sorry?
And from the system. So if the system says I could suggest a nice hotel in these parts of town, that would also split the partitions.
Right. It just makes me wonder about, like, I guess what's left is priors. Like, I'm wondering if I give you this information and you're reasoning your partitioning based on, Chinese versus everything else, restaurant.
Can I come back to that?
Sure.
Because I'm going to talk about that specific point.
All right.
So when you say that the states don't change,
Yeah.
the transition is going to be
The goal, so G doesn't change.
Oh, I believe that. But what about the rest, right?
Oh, they can change. And in the transition model, yeah, no, that's true. No, they don't change either. So you're assuming that there's an underlying sort of set of fixed values for these, and all you're trying to do is estimate them from this sequence of observations. But I'll come back to these issues again, because you're picking up problems with this model, right? So if you want to just think of it, we're hacking various things here to get it to work, that's just fine. And I think so we have a user action model, which is a factored model. I haven't got time to talk about that. So that's the first part, partitioning. Okay, lots of detail in there, but that's the big picture. The second thing is the master space mapping. So we have these partitions and their goal and their grounding states and the user act, and each one has a belief shown by the size of the bar here. So I'm just showing the goal bit, but each of these lines is meant to represent what we actually call a hypothesis for obvious reasons in the system. So you're maintaining sets of hypotheses about what the user goal is, what the last user act is, and what the grounding states are. You're maintaining a list of these, and that's this list. So to do policy optimization, we do some gross approximations. We first of all try to characterize this complete distribution by a fixed length vector, B prime. So this is summary space. And this is something we've been refining, but it consists in the version I'll show you and the one we trialed, this consists of a mixture of continuous and discrete variables. So the probability of the top distribution, probability of the next top distribution, indicator variables, for example, T12 same is that the first two could potentially refer to the same entity. And various other things, last user act, last system act.
Yeah, so now the design summary space now is manually done.
Well, the choice of this, what features to extract is manually done, yes.
So for different applications that you...
No, this is completely independent of the application. These are entirely structural things. That T12 sane just means that if you treat these, I mean, okay, it's generic to a database type information retrieval system. This system knows nothing about east, west, and so on, but it does know what the fields are in the database.
So the schema.
So there's a schema that sits between this and the database, and so if mapping these to the schema and gave you the same set of entities in the database, you'd say they were equivalent.
Yeah, but the size of the summary space determines scalability of the system.
Yes, I guess it does,
So
yes.
somehow, to address that issue, you need to provide some flexibility as to how small summary space eventually you need to have in order to make the system scale.
Yes. This is something we've just started to look at a little bit about the trade-offs in the size of the summary space. But as you'll see, the policy optimization is really quite crude in this system. So what we do is we take this reduced mapping into these fixed length vectors, and then we use a code. We actually quantize this. We have a distance metric on this, and we quantize it. And for each member of the code book, then we associate an action, which is a so-called summary space action. So it doesn't have these arguments. It's just basically the dialogue act itself. And we learn this, we optimize this policy. This is now effectively an MDP rather than a POMDP, and we optimize this using online, actually it is Q-learning. And then we have a heuristic which maps these summary vectors back into master space. And this was originally handcrafted, but in fact we now have a data-driven way of doing this. So this mapping is essentially learnt from data as well. But it's actually not difficult to do. So, for example, if the policy says you should confirm something, then what it does is it looks at the grounding states of the various entities and picks something to confirm, for example. So that's the sort of the architecture. Let me just show you an example of it working. So what you'll see is it's a bit, you won't be able to read it very clearly, but you get the basic idea. This panel here just shows these hypotheses appearing as you speak. The recognizer out trace is in the top here. The output of the synthesizer is here. The recognizer is just a simple off-the-shelf HTK recognizer. The output's a HMM-based synthesizer, so it sounds strangely like Alan Black, for anyone who knows Alan Black. And what you'll see is that the bars here, if you look at the spread over the hypotheses, you'll see, and this was in clean speech, so there actually aren't many errors, but you'll see that the guy, which is one of my RAs, is asking for a venue which there isn't a satisfiable solution.
Hello, how may I help you?
Hi, I would like a bar in the north.
The King's Shilling is a great bar in the north part of town.
What kind of music do they play?
The King's Shilling is known for great rock music.
Are there any bars playing jazz?
I am sorry, but there is no bar that plays jazz music and in the north part of town.
The user wants.
Are there any bars in the center playing jazz?
iSchool is a nice bar in the central part of town and they play jazz music.
What kind of drinks do they serve?
They serve cocktails at iSchool.
What is the address?
Now, these top two hypotheses are actually identical apart from one of the grounding states.
Thank you. Goodbye.
So this represents a very sharp distribution.
Thank you. Goodbye.
And this is essentially zero. It's on a non-linear scale, so we can just see the colours. And don't worry about what the colours are. But so this is basically 100% certain. So in fact, in this example, the recognizer got it exactly right the first time, and it was presumably pretty confident about it. So he effectively got a hit straight away, but then the hit was actually that didn't suit the user, and so the uncertainty came in that way. Now the user changed their goal in that case, but the system just assumes that it simply misrecognized, if you like, the intention in the first place. So the goal stays fixed, it's just recomputing the beliefs. Now that's just that's to give you an idea. If we have a simulated user, which we actually use to train our systems as well, we don't, unlike Nuance and maybe you guys, we don't have access to millions of dialogues. So actually we have a corpus of dialogues, relatively modest number, probably about 1,000 dialogues. And we've trained, as a separate PhD project, we have a statistical user simulator which was trained on the data. And then we use that user simulator both for training and testing. So this is, take this with a pinch of salt in the sense that it's essentially testing on the training data. And what's shown here is comparing the performance of this hidden information state system with an MDP system. So the MDP system is using all the same components, except it's no model of uncertainty. It's always just selecting the most likely state, and it's optimizing the policy based on that in much the same way as the HIS system. But it's not the MDP system's not a broken system in any sense. The guy who made this, it was part of his PhD, and he worked pretty hard, and he was also competitive, so he was certainly trying hard to get the best performance possible. And then this is a reasonable handcrafted system. So learning a policy helps, but in high noise, unless you're tracking multiple alternatives, there's only so much you can do, and the potential, again, of the HIS system is demonstrated by these simulated results. So we also ran some trials. Actually, we've run a couple of trials with students. We had, I think, a total of about, across the trials, about 80 students who worked their way through, I suppose, 20 or 30 dialogues each. And what we did was we basically used, this wasn't a live system on the telephone that came into the lab, but we had extra noise sources. I don't actually remember what the noise source, it was something from that noise database that used to be around a few years ago. So we basically had artificial noise in the background, which we increased the noise level to generate a range of noise conditions. And we'd hoped to reproduce these curves, but the results were not statistically significant if we tried to rank them by error rate. So this is just the result for the pooled data, which is significant, statistically significant. And this is the percentage success we get on the user trial, and the average error rate over all of the dialogues is about 30%.
When you say statistically significant, you mean the difference between...
This is significant.
That, but not between HTC and MDP.
Oh, no, well, probably not, no. No, my significance comment is we can actually bin the dialogues at different noise levels and plot a graph like that. But if we do, the error bars on the data points are so wide that there's, that's not, you can't get nice curves, basically.
Individual bins, right?
Yeah, for each individual bin, yeah.
Could fit, like I'm wondering if
well, we did. We've tried, all sorts of fitting curves, but it's not that. Yeah, we don't feel that confident about it, but we're confident about this result.
So the purpose of adding noise is to make recognition.
Yeah, just to make the recognizer.
Adding more uncertainty there.
Yeah.
Okay. But on the other hand, also this system you talked about earlier also has the summary state. Is that helping or not helping?
Oh, does it hurt us? We don't know. We don't know. We haven't explored that part of the system very much at all yet. I'm going to run out of time, and I need a bit to say a bit more. But yeah.
When you add the noise, do the subjects hear the noise, or that's added?
Yes. Yes. So there's Lombard effects. Yeah. They are suffering. Yes.
How high a noise did you add? You're talking about Aurora database noise?
Well, we changed the noise level so that the error rate, as I said, the measured error rate was varying between 20 and 40%.
And do you notice that subjects do different things if you make it noisy?
Pass. We videoed them if you want to.
So besides the task completion rate, did you have them qualitatively assess the differences? I mean, are these...
Yes, we did. We have a paper that's just come out in Computer Speech and Language with the detailed results if you want to go and have a look at them. And we did do some...
In general, they can notice that that's...
And subjective, there was a...
Subjectively.
Yeah. Although we did another trial. We tried to get over this statistical significance problem with another trial, and there we started to have significant problems. The notion of paying people to do scenarios that are artificial, when you start to look at the results, is very iffy, because people are when there's nothing. If you give them something that doesn't exist in the town, they'll accept almost anything as an alternative. Even though we said, you're really keen on jazz music, they would accept something else. And then subjectively they'd say it was great. I got everything I needed. And you look at the objective results, and they didn't satisfy the criteria we gave them. So we've kind of more or less given up trying to do this kind of trial, and we need to do live assessment. It's probably the only way to do this.
So how do you explain the difference between the POMDP and the MDP? I would expect that the POMDP models the lack of information and ask questions in order to clarify.
Well, and the policy will do that. So the POMDP, for example, will do things like, did you say X or Y?
And the MDP wouldn't?
And the MDP wouldn't, because it doesn't know what the alternative is. Okay. But in fact, that's relatively rare. Where this gains is it also repetition works. So you could keep repeating the same thing over and over again, and it's never in the top 1 or 2 from the recognizer, but it's consistently somewhere in the list. And if you're persistent, then you actually find that the belief in that actually climbs to the point where somehow it gets to the top of the pile. So that's one of the most obvious things when you look at the data is repetition makes a difference.
In a real situation with real data, what kind of human annotation do you need on top of the data itself? Do you need any?
To score these things? To train?
Yeah, I mean, you hope to improve with more data, right?
Yes.
Do you need any kind of human annotation in there?
No. What we need is the dialogue acts in our representation. That's all we need for the training data.
But does a human have to work those out? I mean, if you have a live telephone system and people are calling in,
yeah.
Do you need like something on top of the raw data?
Well, the raw data is it depends what you call the raw data. Our interest is in what the sequence of dialogue acts was, and also what their goal was. That's what we need to know. The user simulator, it uses expectation maximization, so it doesn't need detailed state-by-state annotation. It figures that out for itself. It does need to know what the reward should be, and it needs to know what the dialogue acts were. Can I move on because I? So this was meant as a demonstrator of the potential, right? And it has some severe problems. One is that I skipped the slide that explained how the user action model works, but the user action model's handcrafted. It's not application dependent. It actually uses a set of linguistic rules which define how well a dialogue act matches the goal representation. But it is handcrafted, and there's nothing really to learn. And then we have this problem of changing state. So in the example here, when the system offered a different place that didn't satisfy the user's request, now you can think of that two ways. You can think, well, the user always had this other place in mind, but that's actually not true. Users are guided by whether it exists or not, and they will change their mind, and one really would like to model that. So the obvious thing, so when you look at what we're actually doing here, what we're saying is our fundamental problem is we have a large joint distribution to model. Things like the type of venue, the location, the price, the food. In our system, currently, there are, I think, 12 possible variables here. And so what his system is doing is it's taking the most likely combinations of values, finding their probabilities, ranking them, and pruning off all the unlikely ones. So it's maintaining the top few members of this joint. But then it can't possibly do transitions, because you can't put a matrix on this to get the updated thing, because most of these values are missing. The obvious alternative is just to use a graphical model, because that's how I presented this originally. So what would you do if you had a graphical model? Well, it's going to get big very rapidly. So if you think about the minimum possible dependency, you might say that things like what dialogue designers might call slot values, like location, price, and food. You might say, well, it's either independent, so you might say location, whether it's a hotel or a bar, doesn't matter, but price and food probably depends on what the type of venue is. So you make the simplest possible graphical model that you can do. Of course, this has got its own problems. In fact, I know the east part of town is cheaper than the west part of town, so location does matter. But suppose you did this, then you'd end up with a graphical model, a dynamic Bayesian network, in effect, which looks something like this. You've got something to represent the goals, which might be the food, depending on the type. It's all going to depend on the last system action or system action. You've got you need to somehow get what the user says into this, so you can imagine plucking out the individual components referring to food and representing these as hidden variables. You can have your grounding states as hidden variables. and this is time t plus 1. You can have a few slices of this. And that's kind of the minimum model you could possibly make. And so if you do that for this simple artificial town, you get and convert it to a factor graph, then it looks like this. Well, actually, that's the first of several pages of it. And then you can do something like loopy belief propagation to update the parameters. And if you try and do that with an off-the-shelf LBP, it's very slow. It's quite a big graph. However, you can exploit features of the particular setup, and I haven't got time to go into detail about message passing, but you can do two things. You can partition the values again, just like we did in his system, but this time on a per slot basis. So no point doing an update over all possible values for food if the users only ever mention French and Italian. Just chunk the rest and do these partitions dynamically. And then you can also, instead of having a full transition matrix, you can say, I'm really only interested in whether the goal's changing or not, so you have a constant probability of change. And if you do that, then the compute time for standard loopy belief propagation looks a curve something like this, just plotting time against branching factor. And then, but with these optimizations, you can get something which is tractable. The details don't matter. My only point here is, if you're going to start building these large graphical models, you probably need we need a serious amount of optimization to get them to work in real time. But the big advantage of this is that we can, and this is what we're starting to do now, is we can actually not just model the variables of the dialogue, we can also throw in all the parameters as well. So we can make it not just a discrete network, we can put in the parameters of the distributions, then we can switch from loopy belief propagation to expectation propagation, and we can update the parameters online as well as running the dialogue. And so that's one of the things that we're just starting to get working. The other problem is how you actually build a policy on top of this very large Bayesian network. Again, there are ideas in the literature for doing this, and probably given the time, I should probably not spend long on this. Essentially what we do is we construct a stochastic policy. There's no summary space now. We're building the policy directly on the full Bayesian network, but what we are doing is assuming that there's a very limited set of actions. So we represent a policy stochastically using a softmax with a load of basis functions, and we have a basis function for each possible action, and there's a limited set of these, and then we factorize out the dependency on the various bits of the network into we partition it into components, and then we discretize each component with a very crude binary lookup table. And again, we have a paper coming out very soon in Computer Speech and Language that describes the details of this. And then we use a standard algorithm, natural critic algorithm, to optimize this. So doing all of that, if we actually, and remember there's huge approximations now in the conditioning, we get a performance which actually, I should have overlaid these, actually is very similar to the HIS system. In fact, the performance currently is indistinguishable from the HIS system. The colors have changed because of randomness of PowerPoint, but this is the MDP system from my previous slide. This is the BUD system, and if I'd put the HIS system in there, which I should have done, it would have been almost the same. This is reward against success, but again, the curves are essentially identical. And again, the same user trial gave a statistically significant difference again. The only reason I'm not combining these into one graph is actually because the dialogues were it was done on different days. It's not strictly fair to actually combine them. But the bottom line is it's essentially the same performance. So I'll stop there. Apologize for going on a little bit too long. my basic claim is that, that this kind of framework of POMDP, Bayesian belief tracking, automatic strategy optimization provides a good way to design HCI-type systems. The HIS system, they both, I think, we've demonstrated we can get improved robustness. We haven't dealt with the adaptation problem yet, and adaptation, the work is focusing on the Bayesian network version. The HIS system is still interesting, mind you, because people who build industrial systems are much more interested in the HIS system because they can relate that to what they're doing. They can see that there's an incremental way of going forward here. You can think of the HIS system as maintaining multiple standard dialogue managers in parallel. And instead of taking actions on the best, you're trying to look at the whole bunch of parallel dialogue managers and saying, what would be the best thing to do? And so anything you can think, any tricks that you currently use in your system, you can in principle put them in the HIS system. So as an evolutionary path, that looks interesting. From the point of view of working on adaptation and so on, and online parameter learning, then the BUD system is more interesting. And in the long term, that seems to me the way to do it. So moving forward, we need to develop scalable solutions, particularly for the Bayesian network systems. We need to be able to deal with more linguistic phenomena. We need to be able to deal with multimodal things, but actually multimodal is trivial in this framework. You just add in an extra observation function for all of your inputs, and it's rather easy to integrate them. And there are issues with migrating to industrial systems. Tim has pointed out some of the issues with when his paper with Roberto about how you guarantee performance to a client when your system is essentially statistical and who knows what it's going to do next. But that's where we are, so I'll stop there.
Okay, we have time for questions.
So HIS and BUD systems, in the final comparison, you don't compare HIS versus BUD. I suppose BUD should be better than HIS when you use the Bayesian learning.
Well, they turn out to be currently about the same. Yeah, they're pretty much the same. And that's presumably because the HIS system is able to, so this is coming back to a question maybe Guy or Dan asked about the condition. I mean, the HIS system is not throwing away any conditional dependencies, right? Because it's taking it's sampling the full joint. So some things it does better. It doesn't get, location and price, for example, happens to make a bit of a difference. It models that, whereas it's thrown away in the BUD system.
Both have similar kind of summary space, or not?
Well, the BUD system doesn't have a summary space, but it does have a summary action space, and the summary action spaces are very similar.
But you don't have the summary space. How can you justify the scalability for BUD system?
Well, they're both operating in exactly the same domain.
In a situation where you have real data, not simulated data, how efficiently do these systems use the data? I mean, obviously, data is free if it's simulated, but...
Yes. That's a very good question, and we don't know the answer to that. Clearly, on the simulator, typically, we're talking about the training curves for both systems sort of start to asymptote at about 500,000 dialogues. So, this is, they're getting pretty good by 50,000 to 100,000, but we train up to about 500,000 typically.
And that depends on the size of the problem.
And that will almost certainly depend on the size of the problem, and as we move to richer domains, I'd expect that number to go up. So, but actually, if you look at statistics on nuance calls, and you can look at tell me statistics, I'm sure this is actually not completely, out of the ballpark by any means.
So this is related to, I didn't quite understand the answer to my previous question. Like, if you have calls coming in, you say you need to annotate with the dialogue acts, but does that mean just the acts that the computer took, or the actual real act that the user...
sorry, no, I perhaps misunderstood your question. What we need to do now, because we use our data to train our user simulator, what my answer was what the data our user simulator needs. So currently we have a two-step system. We take data, train the user simulator, use user simulator to train the dialogue system. If the dialogue system was connected directly to real users, all you would ever need to know is what the rewards are. And that just is a question.
No actual annotation.
You wouldn't need any annotation at all now.
But then does the number still hold of like 100,000 or 500,000 or whatever?
No idea. I don't know. Can't do the experiment.
Go ahead.
I think the whole issue with words is interesting because one of the things that I would love to see an analysis of, and I don't know if you published this, is when the system fails, how bad are the failures? Like, it's okay to assign high reward to completing the task, and then everything else gets negative reward, for instance. But to some degree, that's not really true. Some experiences are better than others, right? Even when they fail, right? And you're kind of biasing your system to kind of, do you know what I'm saying?
Absolutely. So this is the sort of thing that Lynn Walker's done and so on, trying to build a model between the reward function and user satisfaction. And then if you could do that, then presumably instead of optimizing this naive reward function, what you would maybe, I mean, I don't know, does Microsoft want to optimize user satisfaction? Let's assume yes, okay. So I guess that's what you'd do.
Yeah.
I mean, and that's an interesting research topic, I guess, but it's not something we've looked at.
When you looked at the failures, I mean, were there any kind of...
Well, yeah, failures...
Because with handcrafted systems, the one good thing that you can do is you can anticipate what the bad things are and kind of make sure they're not as bad.
Yeah, okay, so the HIS system fails, it really does fail. So there's an implementation problem with the HIS system at the moment, is that it's tricky to recombine partitions. And so what you get with a long dialogue is more and more partitions and the dialogue slows down. Okay, and so users give up. The BUD system doesn't suffer from that. You can talk to the BUD system forever. And so in some sense, the BUD system never fails. If you're persistent enough and you sit there long enough, you will probably get the answer. Fail in the sense of not be able to get the answer. Assuming you'll sit there long enough to figure out how to get the recognizers to recognize your voice sufficiently well. It'll just keep on talking. Because all you're doing essentially is updating beliefs in the various slots to the point where you can actually get a match.
But I thought that the reward function penalized the length of the number of turns.
Yes.
Put that in there, you help to minimize that.
Yes, it does. But we're talking about failures, right? I mean, the user doesn't know about the reward function. For them, failure presumably is... And we just arbitrarily chop the dialogue at 20 turns. If we say, if you haven't got it by 20, stop. Yeah.
Does that mean that these dialogue systems never say that they don't understand what you're saying? And wouldn't users give up long before 20 turns?
Probably. And no, it never says I don't understand what you're saying.
It does. That might be an interesting...
We don't have that in our action set. We could...
But that's an obvious POMDP action.
It is obvious, yeah. And
observation is not good enough, and I'm going to try to get more information.
And we haven't got that in. It's probably got surrogate actions. It often, when it gets in a complete messes, it starts to ask you if can I help you with anything else, which is perhaps not the most helpful thing to say. So perhaps it should say I'm not really understanding you, but it's a kind of back off when everything.
So I have a related question. So for a handcraft system, you observe the fact that the users are constantly adapting to the system. Even the users learn how to play with the system after a while. But I wonder, using this kind of a statistical system, actually the system becomes less predictable, and will that actually hurt the user performance, the user experience, because users see inconsistent behaviors from the system? given the same input at a point of time?
So first of all the trials we've done are with people, we deliberately did not reuse subjects. So subjects had, they were all essentially, they'd never used it before, and we sort of didn't let them have enough interactions to really learn very much about the behavior. I guess my answer mostly would be we should be personalizing the user experience, right? So if we figure out how to parameterize these models and we can have something equivalent to the MLLR transform, for the dialogue, then you would if you can recognize the caller, you might plug in the transform. Other than that, the other thing is that, as I said, it takes currently a large number of dialogues to change. So this thing is, if you had this with a real system on live, unless we can figure out ways of adapting much more quickly, which we'd obviously like to do, then it's going to be quite a long time period over which it adapts. And hopefully users would say, yeah, I used that system yesterday, I used it 3 or 4 months ago, I thought it was awful, but it's actually getting quite reasonable now. But
I think it's also hard to tell because, speech, you have to produce the same speech input each time, right? Before you can detect the consistency. And then if you find that there's a particular width in which it's being recognized, well, the system will take advantage of that anyway, so.
Just for a second to the rewards, I'm wondering if there's anything interesting in looking at, or if you guys have looked at how stable this is with respect to assigning rewards, right? So if I assign these rewards that I come up with and I say it's -1 and +20, or if I say -1 and +18, like how stable is the policy?
So
I believe that it won't make a difference for task completion, but I don't know about the perceived.
Well, because it's not clear, so I think you're going to optimize. That's exactly my question. I mean, at least to me, it's not clear. Will it make a difference or not the task completion? Because we're optimizing the rewards here, which is, I don't know, like the mapping to task completion or to the user perception, like how linear or how, varied that is.
So we only ever look at the two metrics we look at is percentage success and the reward. And our reward is essentially the same metric. So
but you could still look, I mean, if you vary, so let's say if is there a way, I don't know, I'm just talking off the top of my head, but is there a way if you vary the reward structure to look, not at, because obviously the rewards that you're going to get are going to mean different things, but to look at the policy. Can you somehow inspect the policy and see, from similar states it takes similar actions or not? I don't know.
Well, under this system you certainly can, because it's basically a lookup table, and you can actually go through the lookup table and see
quantify how much it sort of like
why it seems to be choosing a particular action. One of the things we've done recently which actually improves performance is we actually don't associate a single action anymore with with each belief point. We associate an n-best list, since we use a version of Q-learning, so we have this Q function associated with every belief point. If we look at the n-best list and then you combine the generation problem with the choice of which action to take and say, well, in this context, it's not really obvious how I would do a confirm, constructing a confirm from the current state of my grounding states and so on.
That's an interesting mechanism that will allow you to put some of these heuristics in place that can check against really bad things happening, that Tim was talking about. If you have choices still in the action.
Yes. So we use a ranked list now. And it actually does improve performance quite a bit. Okay.
If there's no further questions, let's give our people.